these. Sometimes I feel like a broken record with these, right? Like I feel like I've said the same thing for probably 3 weeks, yet I still, maybe I need to do something else, right? Because I will still see students that don't apply that technique to this problem. Factor and cancel. And then we have the add and subtract problems. And there we factor to create. Common denominators, right? So that we can add or subtract the terms together. And then finally, we have equations where we factor to cancel denominators. 3 very different types of approaches and problems. And if you mix those up, you're going to really hurt yourself and sort of hurt your grades. And it sort of pains me, right? Because I feel like it's not too hard to identify which of these types you're working with and remember which of those strategies to use. You even have a note sheet, right? If you want to write that down for your note sheet notes, maybe that can help. And if I find that students that do these steps usually do pretty well with the problems. There's still some chances to make some small errors, but you're going to get most of the problem right probably if you take these steps. I won't probably like mix them up randomly on the test just to confuse you, but that is a good practice, is just to see them in sort of out of order. So you make sure you're applying the right technique to the right problem. So 1 over 2x plus 3 over x squared plus 5x. And, you know, I'll tell you the instructions there, although it's kind of a giveaway, right? A lot of times I think people just don't read the instructions, right, and jump right into the problem. But here, our goal is to add. So I know I'm this. I want to factor to create common denominators. I'm not trying to cancel anything out, get rid of anything at this point. I'm trying to create common denominators. And so I do that by factoring. The 2x is already factored, right? And that is a GCF factoring x times x plus 5. And so here I know, right, what the common denominators are, sort of what's missing, right? Over here on this left side, I need an x plus 5. Right, and on the right side, I already have an x, right? So I just need a factor of 2. Okay, so that's the process for creating common denominators, or the easiest process. That's x plus 5, and that's a 6. They're both going to be over the same denominator. So I sometimes won't write this denominator out. But I just want to make sure you don't cancel here, right? That you did all this work to get the common denominator. You don't cancel it out now. We're getting the common denominator so that we can add these together, right? Because these are now the same, I can add those. I get x plus 11 over this denominator. Now, sometimes I'm able to cancel this or simplify this a little bit, right? But here there's nothing common between all these pieces, right? 1 factor on the top, 3 factors on the bottom, right? X plus 11 on the top, 2x, x plus 5. Nothing in common. Right, there's my answer. I would argue that's actually probably the hardest of the 3 types of problems. At least it's up there in the running, because you have to introduce these these new parts to the problem and keep track of what you're trying to do throughout the whole problem. Any questions on that? Questions? Okay. How about 4x plus 8 over x squared plus 3x divided by x squared minus 4 over x squared minus 9. So I'm pausing there because I want you to sort of think about how you would approach the problem. And this is really important in all math problems, is just to pause and sort of think about what's the general structure, or how is this problem going to play out? And then you get into the sort of nuts and bolts of actually doing the problem. Okay. So a lot of times people just jump into the doing of it, and then they get all twisted up and tangled, and nothing works out right. So when I look at this one, I say, okay, this is a division problem. So I just need to factor and cancel. That's really what I'm trying to do here, is factor and cancel. So I'm going to break this down, and some of these parts are going to cancel, and I'm going to change this, right? Flip, because it's division. So like that's the general framework that I have in my head of how I'm going to approach the problem. Nothing like this one, really, right? This one had common denominator stuff. I don't need any of that here. I just need to factor it and cancel. So I want to be, a little careful as I factor. These first two are both GCFs. I'm going to change it to multiplication in one step. This x squared minus 9. I know how that one's going to factor, and the x squared minus 4 is going to factor. So I factor everything, and now the multiplication is really, it's just canceling. And I can see here I have an x plus 2, and I have an x plus 3, and that's the best I can do. Which gives me this. Stop. That's as far as I can go. That's what I'm looking for, right? Really a reduced or simplified problem in the end. Okay. There you go. Cut that. A surprise. All right. So again, the first thing I notice is that this is an equation. And whenever I have an equation, I want to get rid of the denominators. Right. So in my mind, I'm imagining, okay, I'm going to start by eliminating the denominators. That's going to give me some better equation that I can hopefully solve. Now, to do that, I am going to have to do a little factoring here. Right. So if I factor out the 3x minus 9. Right. So now I can see what's common to all three of those denominators. There needs to be a 3, an x plus 2, and 1 x minus 3. So what I like to do is just multiply each piece by that same thing. You can do this in other ways. You can kind of write it out and distribute it or other things, but I kind of like to just go right to this step. And maybe you feel like, oh, I don't need to write that same thing each time. You don't, but it sort of helps, really, I think, because when you cancel, then you can see directly what is left over. Otherwise, you've got to kind of distribute it and try and remember as you're canceling and distributing. I feel like that makes life harder, and I like to keep life easier, right, when possible. So here I have a 2 times a 3, so I'm just going to multiply that out first. That's the quickest. And here, right, the 3 and the x minus 3 cancel. So I get 5 x plus 2. Right? And this is where I want to be, right? I'm not trying to add these together. That's maybe the most common error I see people make, is they add these two together. Even if they do it properly, they end up still with an equation, and then they often are like, oh, I don't know what to do now. I finished adding them together. Well, that wasn't really what we needed to or wanted to do with the problem, right? So don't do that. I think that's more work than you need to. Right, this one turns out to be a nice linear equation. Right, subtract that and I get 4x equals 22. So x equals 22 fourths, which is the same as 11 halves. And then I'm going back here because I want to make sure I don't make any of these denominators 0. Well, 11 halves is not an issue here. Right, 3 or minus 2 could be an issue, but 11 halves is fine. Yeah, there we go. Okay. Any questions there? Questions? Okay. I hope that's a good sign. It's very likely that it is. But if you haven't gotten to these problems yet, just keep these in mind and get some good habits going. The last thing that I wanted to make sure to show you guys for today was a work problem. So this is in the application section, and there are problems involving work, and they're a little bit, let's say, specialized in that the equation that you generate is not one that you would probably come up with just on your own, I think. But it's a pretty easy pattern once you see it. So here's an example. Anne can create a landscape plan in 6 hours. And her apprentice can do the same plan in 8 hours. How long will it take if they work together? Oops, they work together. And this is actually like a pretty realistic problem. I guess there's a couple assumptions here. First of all, you have to assume that Anne and the apprentice can both work in sort of the same speed and the same efficiency if they're working together than if they're working alone. And that obviously may or may not be true in reality, right? But if we assume that certain conditions, that's not crazy. And this comes up whether you have like Anne and an apprentice, or whether you have like two hoses that are filling a tub or a pool, or you have two conveyor belts moving a certain amount of gravel, or two things that can do something kind of at one speed on their own. How fast does it take them to do that thing when they work together? So it's a realistic problem, right? That has some real applications to it. And it's also not like totally intuitive. So be careful here, because the answer is definitely not 7 hours, right? Sometimes people are like, oh, well, just in the middle. No, no, no. I mean, it's two people working on the same plan. So like if it was Anne and her twin both working together, it should take them 3 hours, right? Because they would do half of it they would work exactly the same speed, and they would end up doing half of it exactly. And so they would both work 3 hours to get half of it done, and they'd get the whole thing done, right? And if it was two apprentices working together, then that should take them 8 hours, right? Or sorry, 4 hours, because each of them would again work exactly the same speed and get exactly half of it done. So the time that Anne and her apprentice should be somewhere between 3 and 4 hours. But they're working the same amount of time. So Anne is actually going to get like more of the plan done than her apprentice, because she works a little faster. And it's not really clear how much more she's going to get done, or how we could figure out or set up an equation for that. And that's what makes this problem a little bit sneaky, right? It's like, okay, it sounds kind of simple, but the answer is not obvious. So, let's call this T, right? That's what we're looking for. Anytime we do an application problem, we like to define the variable. We're looking for T, the time it takes them to work together. But again, it's hard to set up an equation directly. And the special technique here is to look at how much of the plan do they complete in 1 hour. Now, again, this doesn't have to be hours. This could be minutes, or any kind of time increment that's being used. So if Anne does a whole plan in 6 hours, then definitely she has to do 1/6 of the plan every hour, right? Because 6 hours, 1/6 each hour gives you a whole plan, right? One. And the apprentice, well, they have to do 1/8 of the plan each hour. And after that hour, they've completed some portion of the total plan that they could do together, right? Because if Anne does 1/6 of it and the apprentice does 1/8 of it, then they should be sort of doing that portion of the total plan. If they work together, let's say it took them 4 hours, then it would be 1/4 of the plan, right? If it took them 3 hours, it'd be 1/3. If it takes them T hours, it's going to be 1/T. So this is like the amount of the plan they complete in an hour working together. And that amount has to be equal to the amount that Anne gets done plus the amount the apprentice gets done. And this format is how these work problems are structured. So that's how you want to look at these problems. You may sometimes know how long it takes them together and not know how much Anne or the apprentice does, or maybe some of these are some variables in here. Maybe you don't actually know the apprentice either, and you have some other structure, but it's basically 1 over this amount plus 1 over this amount equals 1 over the total. The nice thing about these is that they're very straightforward problems to solve once you have them set up. I need a common denominator here because it's an equation. turns out 6 and 8, the common denominator is 24. So 24t, 24t, 24t. So that's going to give me what? 4t plus 3t equals 24. Seven t equals 24. So t equals 24 over 7, which is 3 3/7. Right, and based off of our estimate before, that is a reasonable number, right? We thought it should be somewhere between, or I thought it should be somewhere between 3 and 4, and this is certainly between 3 and 4. Okay. Any questions there? Any questions? Okay. So, you know, as always, the goal is to get your stuff done on time and then move on to the next section, right? So these things always go better when we can get started on the next section sooner rather than later. For you guys, what you'll find is our next section here is dealing with radicals. So square roots and cube roots and working with radicals. And I'll tell you the first kind of 3 homeworks there make a big difference in terms of how the rest of the course goes. So, or the rest of this section goes. So really make sure you get started on those first 3 early and, you know, continue what you're doing. I would encourage you to bring questions. It's more fun if I can help you through some things here. But if you're getting that help other places, that's perfectly fine too.